YouTube, this is UMills03. Now we're on to lesson 31 in the Python curriculum. We're well over halfway through, and we're pretty soon going to be talking about something called object-oriented programming, but there's just about 2 more lessons that we need to cover before we get there. What I wanted to do in this video is review decorators one more time, but there's a new topic that we're going to bring up in this video, and it's the topic of recursion, and basically it's when a function can call on itself multiple times. And it's sort of a confusing and trippy concept, but basically what it allows us to do is repeat a block of code, and we can basically run a function or repeat a task multiple times without needing to use a for loop or a while loop. But what we're going to do is remind ourselves that decorators are functions that are used to enhance, some main function f, and we know that the decorating function accepts f as input and returns an enhanced version of f. We saw that with the print favorite function as well as the division function from the previous video. The decorating function, D, has an inner function which accepts no inputs. This is actually not necessarily true. We saw in our division example, our better div, right? And so I actually made a slightly different example here, but if we scroll down, we can just take a look at this right off the bat. Well, let's look at the print favorite first. So this is the one that we started with, and this is a void method. Okay, so print favorite doesn't return anything. It just prints something, right? But by virtue of going ahead and having the @ symbol and then the name of this decorator, we say that instead of just using print favorite's original implementation of the function, we're going to use the enhanced version, okay? So wherever we see f, we're going to stick in print favorite, and we're going to be using the decorated version of print favorite rather than print favorite itself. So hopefully that's clear to you. And you want to be careful with the syntax here, okay? So there's just one inner function. And then since this is a void function, you wouldn't say return f, you just say f, okay? So then that would be different from down here. Remember in the subtraction example, subtract them returns a number, okay? And so that would have to be, it would have to be returned in the inner function of the decorator, okay? But for this inner function within this decorator, you just call f because f is void. Okay, but you are going to end up returning an enhanced version of the function, okay? So, even though f is void, wrap f is returned, okay? And so we saw that for both the void case where we were just basically, printing a couple of strings, and also the, the more mathematical case, I'll say, in the previous video, we were doing it with division, and I said, well, we can do it with subtraction too. It's very straightforward. Instead of just saying a over b, you would say a minus b, and this has the same effect, okay? So what if someone naively tried to say subtract them of 8 and 10, okay? So that would give us -2 if we're doing the pure subtraction. But as a result of what we instructed in this method, if we were to make Java docs, what would we do? We can make Java docs for a decorator, okay? And then what you can do is you can actually see that sometimes these fields are already populated for you, so you can go ahead and get reminded that you need to specify parameters and return values. But we can just start from scratch, and we can say this decorator accepts a main function and returns an enhanced version of the function by flipping the two numbers to subtract if the bigger one was going to be subtracted from the smaller one, something like that, right? Just give people an idea of what's going on. It doesn't need to be Shakespeare literature, right? But what you could do is you could say parameters, and then for this one, you'd just be talking about a main function, okay? So here, you're actually going to have 2 sets of Java docs, okay? Because technically, if you wanted to be formal and you wanted to have good etiquette, you would indeed need doc strings for the inner function too. So you would say main function, a function to enhance, okay, like presumably, something like that, by flipping its inputs, okay? So this is kind of general, right? It's called better subtraction here, but you could have just called it decorate me, okay? And then you could decorate a subtraction. You could decorate a division, because the only thing that this function does is switches the ordering of the 2 inputs into main function, whether that's division, whether it's exponentiation, whether it's, some kind of mathematical operation, presumably is going to happen. Okay, and then you could go ahead and say, okay, so let's see what happens here. So now what you would do is you would say returns, and then you could say basically like inner, the result of the inner function within the decorator, something like that, right? And then you would have to come down here and you would have more Java docs, right? So you would say basically this inner function accepts 2 inputs, which were inputs to the original function that was fed into the decorator, and it returns, what would it return here? So it returns the result of that original function with the inputs swapped if the first is less than the second. Okay, so something like that, and then you would say param A, the first input or something like that, and then param B, you would say the second input, and then return the result of, you could call it F if you want, you know, or the main function, the result of main function when A is mandated larger than B or something like that. So that would give you, that would be formal documentation. And like we talked about, if you scroll over this inner now, you can see the documentation here. So then you could go ahead and give you the description, and it will also indicate the parameters and the return value. So hopefully that's helpful for you to see, and that's an example of documentation. And if you become a software engineer, your manager is going to be looking for you to write comments like this. Okay, and then so we already know how this works, and so it's an enhanced version of a function. So we accept a function and we manipulate its functionality in such a way that the original function can do something better, do something a little bit, we behave a little bit more how we might want it to behave, or just do something that goes above and beyond the original implementation. A recursive function is a function that calls on itself to execute its contents multiple times, okay? So this is an alternative to iteration, or a while loop or a for loop is used, okay? So basically when we have recursion, a function is calling on itself over and over again with simpler and simpler inputs, okay? And it reduces down to a base case most of the time, like in general, okay? And only the base case of the recursive function has a known value, and all other values, all other f of x's or f of n's, need to be found from known values of f of x or f of n. And you need to build up recursively. It's like a building block. You need to basically develop the values of the function or the values in the sequence one at a time, rather than just being able to stick in a value of x. Okay, so let me give you an example. Let's think about a function f of n is equal to 4n plus 3. And obviously we could make a regular function out of that. We could make a lambda function out of that. It's very straightforward, right? It accepts an n and gives 4 times n plus 3. Okay, but then what we could do is we could come up with a recursive version of that function. So how do you build f of n? How do you get 4n plus 3? Well, what you would do is you would say that the first term, you know, if we're starting at index position 0, it's just 3, okay? And that's a critical piece of information, because now the only thing you need to say is that then for every term after that, the next term in the sequence is just going to be 4 more than the current term. Okay, so what's f of 1? Well, it's just 4 plus f of 0. So 4 plus 3 is 7. What's f of 2? Well, it's just 4 plus f of 1. So 4 plus 7 is 11. And that's the effect that the 4n here has. Okay, so 3 here is basically taken, it's interpreted as the initial value. And then the 4 here is sort of like the increment. It's the slope, right? It's the increment in f for each of the values of n. So hopefully that makes sense. Okay, so we're going to talk about some mathematical functions and sequences that are recursive. So the first one I wanted to talk about is the factorial function, and we're actually going to implement it in 2 different ways. So what we're going to do is we're going to say iterative factorial of n. Okay, so this function is an iterative implementation of the factorial. Okay, and we should try to remind ourselves of what factorial is. So remember, if you basically have something like 4 factorial, you know, that would be 4 times 3 times 2 times 1, okay? And that's not the formal, that's actually not technically the definition of factorial. We're going to see the formal definition in a second, but for now we can just sort of have this simple, straightforward understanding, okay? And one of the things you might also need to remind yourself of is that 0 factorial is 1, okay? That's just by convention, and we're going to see why that was mandated in a second. So what we're going to do is we're going to say something along the lines of, it would be something like result equals 1. So this would be like the default result for n equals 1, for example. So we know that basically 1 factorial is equal to 1. And then what we're going to do is we're going to say something like r equals list of range of 10, or list of range of n plus 1. So let's think about what list would be of 0, 1, 2, 3, all the way up to n, okay? Because we said that, you know, n plus 1 is not included, you know, as that extreme, okay? And then what we would do is we could basically say r dot remove of 0, or r equals, if you want to use list splicing, one of the things we said that we can also do is r equals r of 1, and then just start out that at the first index position. So this cuts out 0 because we do not want to multiply our result by 0, okay? And then what you would do is you would basically say for s in r, okay, and you would say result times equals s. Okay, so you would just multiply every value all the way up to n. So if you were saying iterative factorial of 4, it would do, okay, result is equal to 1, and then it would say result is equal to result times 1. Result is equal to result times 2. Result is equal to result times 3. Result is equal to result times 4. And that has the effect of multiplying the numbers 1, 2, 3, 4 together. And then we just have to remember to go ahead and return the result. Okay, so now if we go ahead and run it, print, let's go ahead and do 4 factorial. So iterative factorial of 4, and then we can go ahead and run main.py. And then we need not define result, return result. Okay, brain fart. So now you can go ahead and run main.py and you get 24. But now what we want to do is we want to make an iterative implementation where instead of using a for loop, we are literally going to use the factorial function itself. So let me show you what I mean by that. What we're going to do is we're going to say define recursive factorial of n. Okay, and you can specify Java or doc strings on your own. So I encourage you to do that on your own, but those are kind of take up a lot of time. So what we're going to do is we're going to basically say if n is equal to 0, we're going to return 1. Okay, so this is called the base case. Okay, so recursive factorial only specifies one value for that function within its definition. It only really returns one like concrete constant value. And if you're plugging in anything else other than n equals 0, if you plug in recursive factorial of 8, it's going to need to do 8 steps of work because it's going to need to work its way back down to a base case. And you think, well, 8 steps, that seems like a lot of work, but this is 8 steps too. If you do a for loop, this is still doing a multiplication. It's still doing an operation. It's still doing something mathematically 8 times if you plug n equals 8 into either of these implementations. So now what you would do is you would say, otherwise, if I'm trying to find the factorial of something bigger than 0, the way that the factorial function is actually defined is that n factorial is equal to n times n minus 1 factorial for n greater than 0. And then we say n factorial is equal to 1 for n is equal to 0. So 0 factorial is 1. And then this is the definition of the factorial. So hopefully this makes conceptual sense to you. But we say that the factorial of a number is just equal to that number times the factorial of the previous number. Well, what's the factorial of the previous number? It's the previous number times the factorial of the previous. Well, what's the factorial of the previous? It's the previous. And you can see how you're going to be multiplying all those terms all the way back down to 1. Okay, and so now what you're going to do is you would say return n times, and then you literally are going to call the function again. You're going to define recursive factorial by recursive factorial. And this is kind of trippy because then the question is, well, what's recursive factorial? And the only thing you do, you don't overthink it. You're just going to go ahead and run recursive factorial for the next version of n, And here, so you'd be talking about n minus 1. Okay, but you keep subtracting 1 from the input of the recursive factorial. Eventually, you're going to work your way back down to this base case. You are going to make n equals 0, and then at that point, by the time you get there, you would have had all those building blocks. You would have multiplied all those values of n along the way, and so this is going to work the exact same way. I'm going to turn this into a Boolean expression where I ask Python to tell me whether or not it's true that if we run the factorial with the recursive method, then we would get the same result as if we ran the factorial with the iterative method. So now let's go ahead and run main.py, and it says true. Okay, so that's kind of comforting to know that we have 2 completely different ways of doing the same thing. Okay, but conceptually, they're doing basically the same amount of work. But this one uses a if-else statement and makes multiple calls to its own function. And this one uses a for loop, and it just runs the function once, but it's going to spend a lot more time with that one function call. Whereas these have much quicker function calls, but there's more of them to do. So hopefully that makes sense to you. Let's try another example. We can think about the Fibonacci sequence. I'm not sure if you're familiar with this from mathematics, but essentially the way that it's defined is 1, 1, and then all numbers after that, and then every term after that is the sum of the previous 2 terms. Okay, so what we're going to do is we're going to build up the Fibonacci sequence. So we're going to say define Fibonacci of n. Okay, and so basically this function returns the nth Fibonacci number. So for example, we could say Fibonacci of 1 is 1, Fibonacci of 2 is 1, Fibonacci of 3 is 1 plus 1, which is 2, Fibonacci is 4, which is 1, Fibonacci of 4 is 1 plus 2, which is 3, right? And then pretty soon this is going to take off, right? Now, so now if you go up 1 more, then you get 5, right? And then you're going to start skipping. So then it'll go 8, 13, 21. It's going to accelerate a little bit. But then the way that this is, so then this is exactly how it's defined. You just go ahead and specify two base cases, okay? Because this rule depends on two previous terms. And so you need to specify two values in the definition. What you need to do is you need to basically say if n equals 1, and let's go ahead and index this by starting at 1, okay? I know that in Python we normally start at 0, but let's think of just in English, just in common terms, oh, what's the third Fibonacci number? Okay, so we're not going to start at 0. Let's start at index position 1, essentially. So we say if n equals 1 or n equals 2. Okay, so these are the two base cases because our terms depend on two previous terms. So that means we need two base cases. Hopefully that makes sense to you. Okay, and then what we're going to say is return 1. Okay, because that would be basically the result of Fibonacci for those first two values. But otherwise, what we need to remember to do is we need to say Fibonacci of n minus 1 plus Fibonacci of n minus 2. It's just going to sum the previous two terms in the function. So if you want Fibonacci of 4, it's Fibonacci of 3 plus Fibonacci of 2. Well, what's Fibonacci of 3? It's Fibonacci of 1 plus Fibonacci of 2. Well, I know what those two are, so now I need to work my way up, and I'm going to be adding up different combinations of these previous terms to work my way up to the term that I'm trying to find. So hopefully that makes sense to you. And then you can just go ahead and try it. So we have this sequence, right? So 8, 13, 21, 34, 55, 89, 144. So I guess this would be the 6, 7, 8, 9, 10, 11, 12. Okay, so we should be expecting here essentially that the 12th Fibonacci number would be 144. So now if we can go ahead and run it, and indeed we verify that result. So hopefully that makes sense to you, and we want to see a couple more examples here. So let's just go ahead and do a couple more examples. Well, we have time for one more. Let's do a void method. Okay, so here's what we're going to do. We're going to say define print stars of k. Okay, so what this function does is this function accepts an integer k presumed positive, and prints not returns, but prints that many of character v. We can say print v. Okay, so here's what it's going to work. Here's how it's going to work. What we're going to do is we want to print the character v, whether it's a string, whether it's a a list, it could be a Boolean or something, or a tuple, right? But it could be anything, and we're going to print that thing, that object k many times. So here's what we're going to do. We're going to say if k equals 1. Okay, so if I already if I get down to k equals 1, I just want to go ahead and say print v. Okay, and that's not that hard. But then if you say otherwise, if k is bigger than 1 or something like that, what you could do is you would say print of v, and then you would do print k of k and v minus 1. Okay, so then you would just go ahead and print, you would print one fewer of v after having printed v one time. Okay, so this allows the function to work down closer and closer to k equals 1, which the function knows how to evaluate, right? At that point, you wouldn't keep iterating, you wouldn't keep calling print v over and over again. It's print v, not print k. Okay, and then you could say, yeah, otherwise, if k is greater than 1, right? So then hopefully that makes sense to you. And then what we would do is we could go ahead and take a look at this, right? So then we can say, I'm not sure what the issue is here. It says colon's expected. I'm pretty sure I had a colon. I guess what we need to do is, let's just go ahead and try running it. elif, right? Sorry, elif. I was thinking Java syntax, right? We got to be careful when we go back and forth between two programming languages. So elif, right? And then we can go ahead and try it. Let's go ahead and try to figure this out. So now what we can do is we can say, what we're going to do is we're going to say my list. We'll try a tuple. Let's try a tuple of lists. So let's do 6, 7, and then we'll do 1 sub. Okay. So that's a tuple of lists. Okay. And so what we're going to do is we're going to say print v of 4 and my lists. Okay, so now we can go ahead and run it, and hopefully we see that list printed on the console 4 times. So let's go ahead and take a look at what the issue is here. So we have k, k and v minus 1, right? So k is what's keeping up with the number of times that we're printing v. Okay, it wouldn't make any sense to subtract 1 from a tuple. We're subtracting 1 from the integer that represents the number of times that we print v. Okay, so be careful on these inputs. Maybe you want to call these things something a little bit more descriptive so you know that you're talking about, right? You could call k like number of times, and you could call v like symbol to print or something like that. But anyway, it would not be v minus 1, it would be k minus 1. So now you can go ahead and run it, and indeed we get main.py, and we get the list of tuple of lists 4 times. So hopefully that's clear to you, and we'll see more examples in the next video. From Emails03, thanks for watching, and please subscribe.